Now that I've showed you how to fit a scikit-learn model, what we fit was a regression model. So the next step is evaluate the model. So you always want to, whenever you fit a model, you need to worry about and spend quite a bit of effort evaluating the model. And we'll go through several different ways to do it. At this point, we're just going to use a really simple set of basic evaluation methods, and they're specific to regression models. So on my screen here, I've created some code to compute and print some commonly used metrics for regression models. So it's like mean squared error, root mean squared error, mean absolute error, median absolute error, R squared, and adjusted R squared. And I'm getting these all from scikit-learn's metrics package. And you see I can run scikit-learn metrics. I just loaded it as SKLM, like mean squared error, and I give it the true label and the predicted value. And I just go through and do that for each one of these. And for example, here I just need to take a square root. So I have to do a little bit of processing. To get the adjusted R squared, I have to adjust by number of model parameters minus 1 and the shape of the data frame minus the model parameters. So pretty easy to do here. So let me just run that, and we'll see for our linear regression model we've created. And we see we've got, now remember this is for the automobile prices, and so we've got pretty low or log automobile prices. So it's important to keep in mind we're evaluating on the log prices. So we've got the mean squared error is just 0.02, and the root mean squared error, of course, is considerably bigger because it's the square root. Median, mean absolute error, and median absolute error pretty close. These are all pretty similar. R squared is pretty high, 0.92, which means we've explained a fair amount of the variance of that original data. Remember, R squared is just effectively 1 minus the ratio of the variance of the residuals divided by the variance of the original label value, which is the price. Now, but adjusted R squared, because we have a fair number of model parameters, this n params is fairly large, and the number of data samples used in the training data is fairly small, there's a big difference there. So that's something to keep in mind. And what that means is that we don't have actually that much confidence in R squared or adjusted R squared because of the bias adjustment. So those look promising, but you really want to drill down and you really want to look at the histograms of the residuals. The residuals, of course, being the difference between the predicted and actual values. And so let's look at that. So again, remember we're on a log scale here. Here's 0. Ideally, we want all these residuals really close to 0. And they're not too far apart, but you do see there's some asymmetry, some dispersion in this. So it's not ideal, but it's not bad. And the other thing is for a linear model, you really want the residuals to have a normal distribution. That's sort of one of the assumptions of a linear model. And we're pretty close, but clearly we're a little off that assumption, but maybe it's not so bad. Another way to look at that relationship is with a quantile-quantile plot. So let me just make it and then try to explain it. It's easier than trying to wave my arms. So this is the quantiles of the residual on the vertical axis. This is the quantiles of a standard normal distribution on this axis. So if these residuals were perfectly normal, they would lie on this red line. And you see they do not. They're a little bit curved, kind of a little bit S-shaped. So, and that reflects this behavior here where we have some asymmetry and almost a second mode of these residuals. So, but it's not bad. It's a little off a normal, the ideal normal residuals we want, but it's not night and day off. And then there's another plot. This is a really important plot. It's called a residual plot. And if you don't do any other plot with your regression model, at least do this one. And so we're plotting the predicted values, the score, versus the residuals. Let me go ahead and do the plot, and I'll explain what's going on. So here's the predicted values. Remember, again, we're on a log scale. That's why they're all single or double digit. And here's our residuals, again, on the log scale. Now, what you don't want to see in this plot is a lot of structure. You don't want to see something like a cone-shaped dispersion or something like that, or a big U of the points. If you see definite structure, that means that somehow your model isn't picking up all the information in the data, and your predicted value, the residuals, are dependent on the values that are actually being predicted. And that's bad. Over the years, statisticians have said the ideal, if you have a lot of points in these residual plots, the ideal residual plot should look like a big, long, fuzzy caterpillar with some fuzz up and down. You'll have residuals that'll be away from the zero line here, but they won't have any structure that you can see dependent on the predicted values. So that all looks good, but let's do one last plot. So remember, we've been doing all this on a log scale. So now we're going to exponentiate our scores and exponentiate our transformed test labels, and we'll do another residual plot. And this one doesn't look so good. What it says is, and you see this is now back in units of dollars for the price of the cars. You see the residuals get noticeably bigger for more expensive cars. So our model's doing pretty well predicting the price of inexpensive cars, not so good predicting the price of luxury cars. So that's a quick run through on evaluating regression models. The take-home messages are, first off, you need to look at several views of this. Don't just print a few metrics like root mean square error and say, oh, yippee, I'm done. Look at multiple metrics, see where they might conflict, where you might have something like the fact that the adjusted R-squared was very low compared to the R-squared in our case. Look at the residuals. You really want to look at the residuals in a regression model, because the regression, if the regression model is a good model, the residuals should be well-behaved. By well-behaved, I mean close to a normal distribution, which we more or less had in this case, and the residual plot of predicted values versus residuals shouldn't have any noticeable structure. Now in the logarithmic transform domain, that looked pretty good, but when we untransformed, we could see that really we're doing a very good job of predicting the price of inexpensive cars and a pretty poor job of predicting the price of expensive cars. So we may need to go back to the drawing board on our model and figure out what to do about that.